Okay, thank you very much for inviting me here. It's my great pleasure. I'm very delighted to join the team to talk about resilience. But in fact, my background is GIS, and as Professor Chong just talked about, so I'm going to talk more about GIS here, and I hope you enjoy it. Specifically, I focus on one of the major issues. It's called spatial variation. Then I'm going to first show you some pictures, some maps, to demonstrate the existence of spatial variation. And then I will let you know how we measure it. And finally, we will talk about some opportunities and challenges. First, let's have a look at the maps showing spatial variation. So normally, we collect environmental samples, and then we are going to produce those maps. For those maps, you can easily see that they are not homogeneous. You will see some high values or some low values at the regional level. And then this is also regional level. This is Northern Ireland. And then this is also regional level. It's a city in Galway. It's a small city in Ireland. And this is at the field level, just within one land. It's a fairly small area. And we show it to non-academic people, to specific to environmental managers or whatever, to show them that's some pollution, whatever. I think that's the easiest way. But specifically, you can see the variation there. I stick to the word variation. And this is quite important. That's within the field, we have different levels of fertilizer requirement for agriculture. In fact, that forms the background for one of my commercialization project, which has just been finished. And in Galway, in Ireland, we have set up a spin-out company to do that now. And perhaps you have never seen that, many of you. That's a very micro-scale variation. It's at a sub-millimeter level. We get the variation of chemicals. Specifically, we get phosphorus and sulfur. And also, this is another way for us to get the variation map. In fact, it's membrane. It's called diffusive ingredients, diffusive gradients in thin films. So we can easily get those images. Anyway, I'll just demonstrate to you the spatial variation exists at very large scale, regional, to very micro scale at millimeter level. So that's the fact, and there are many factors causing it anyway. Now, how do we measure it? It's there, then what can we do? Okay, first, the easiest way to measure it is just visual. Okay, we have already done that. Okay, that's the easiest way. Second way, I'm going to talk about it. That's using statistics. Now, when we have a data set, how do we measure variation? We get minimum, maximum, value range, whatever, standard deviation. So that's how we do, okay. But we get only one value for a data set. But here, I use local statistics. We are going to get a variation map. So what's that? So for example, have a look at this one. That's one of the chemicals. Anyway, everybody knows that. So you get high values there and very low values there. In fact, I expect there's a very strong variation here. You can see that two major parts. If I can visualize and show that, that will help us to identify the influencing factors. So you can see you get different areas. In fact, I really want to see that cliff there. You get a plateau, get a plane here. How can we see that? The method is like this. If we calculate coefficient of variation, okay, that's one of the statistical parameters. Normally, we can get all the data, 6,000 samples, then you calculate the value, right? But here, what I do, I only calculate that area and put a central point there. So you get low values there, and you can see this value get fairly low variation there. If you move the window, variation will increase. You can get some high values there. And if you keep moving, this point, if it's in the center here, you will get very high variation value. Believe or not, I believe you. I think you trust that because we got half of them very low, half of them very high. So you can easily show the variation. In fact, to do it in this way, we will see it. So it's a very simple idea. Just CV value coefficient of variation. But if we do it on a map, but this helps us to identify which area are more variable. In fact, that signifies the significant change of controlling factors. That helps us to identify environmental factors. And in fact, that's the change of two major rock types. So that provides us concrete conclusion when you analyze environmental parameters. And we can play more games, different shapes of the area and different size. For example, different size, then you can see different maps. So with the increase of the window size, you see larger patterns, and smaller patterns, you see more details. That's a very effective tool. So this one is just local statistics, and you can easily implement using GIS. That's number one, okay? Number two, how do we measure spatial variation? Another idea is to use spatial outlier. So when we get data, we care very much about an outlier. Yesterday, I was in the environmental risk assessment conference. We care about pollution, so we want to identify those sites. Normally, we just rank the data. The high values higher than a certain threshold value, you call them polluted. But here, in fact, I want to tell you another idea, a spatial one. We compare the value with the neighbors, and then it will help you to identify those hidden outliers. That makes sure that you get more information from your existing data. Specifically, we're interested, for example, a high value and a low value area. Then how do we do that? So this, I use an example of urban soil in Galway. And I took 166 samples, then we map it. So visually, we can see some potential outliers there. We see clusters there. That's a high-value cluster, low-value cluster, and those outliers. Visually, we can see them. In fact, we can do that statistically. So we can see that the method is called LISA, Local Indicator of Spatial Association. I borrowed this idea from a guy studying spatial economics. They are interested in hotspots in economy. So I apply this idea to environmental science. And that's the function. I'm not going to go to details of this one, but if you're interested in it, just write this one down, local Moran's eye. Specifically using this parameter, we're able to identify high-value clusters, low-value clusters, and high-value and low-value area, that's outlier. And low-value and high-value area, that's an outlier. And the fifth one is not significant. So based on some kind of calculation, we will identify if that's significant or not, statistically. After that, we're able to see them on the map. So we get high-value clusters in the urban area, and low-value clusters in those in the suburban area. And also we identify some of those outliers. So this method helps us to identify those spatially significant outliers and clusters. That helps us to identify those environmental features. In fact, to quantify variation, if we go back to the word variation. And then we can easily link them, and we will see those visually identified ones, so we can also see them there. And also we identify some of them, we couldn't hardly see them, but statistically we can identify them. And this idea can be used to find mining sites. Specifically in China, at a geological survey there, they already found more than 2,000 mining sites based on geological survey using geochemistry. I have suggested to them to use the idea of a spatial outlier, trying to find out more hidden mining sites in China. I think it may also work here in Korea, and also find the hidden contaminated sites in Korea based on our national survey database or database from various sources. So that's some kind of game you can play with. And specifically in Ireland, we study outliers or clusters of bonfire in urban area because Ireland is so clean. I think my colleague from Australia knows that. It's a very clean air country with very little pollution. But one of the pollution sources is bonfire. So we use to analyze bonfire. And also in London, we use the concept to analyze rare earth elements in cities area of London city. And we can see the patterns of clusters. And we can easily link that with geology, even in a very urbanized area. And also, we analyze phosphorus in the urban area. We can link it with water and built-up area. And in fact, this is one of the points I'm very proud of that. This area, we can hardly see any hot points or cool points there. It's related to the highest tide of the River Thames. And normally, if you just visually see it, you can hardly find that point there. The last method I want to talk about to measure spatial variation is variogram. It's called spatial correlation. This concept is important when we produce maps because it has been quite often ignored by users who do not understand geochemistry. Specifically, we have sampling sites in Ireland. Well, the same in Korea, if we have that. I believe we have. Then we calculate the difference between neighboring samples. If the difference is small, then they are correlated. They have better correlation. If the difference is high, we see that they have a poor correlation. And the method is called variogram. In fact, this is the parameter to input for spatial interpolation called kriging. I'm talking about the earlier step for kriging. It's a variogram. And this provides quite a lot of information there, and it's quite often ignored by people. And specifically, what we expect is that with the increase of distance between points, then we expect their difference increase. But does not always happen. For example, this one, available P. If it shows in this way, with the increase of the distance between points, it does not show the expected one, then that's a huge problem. What problem is that? Spatial interpolation is not allowed. I'm going to talk a little bit more about that, but this is quite often ignored, so I want to highlight this issue here. And in fact, when we do the kriging, when we get the maps for Ireland, I'm quite happy with other parameters. Altogether, for the National Geochemical Atlas of Ireland, we produce quite a lot of maps. pH, whatever soil organic carbon, and the total P. I declined to produce spatial distribution map of available P. The reason is that I believe the variation is too strong for me to produce spatially interpolated map. I declined to perform any interpolation. And if we do not understand variogram, do not understand the assumption for spatial correlation, pure technicians will definitely produce that map. And when I declined to produce this map, the funding agency, Irish EPA, and the Chaosheng Irish Agricultural Institute, they were very happy. They were very supportive to me because we do not want to provide misleading information to the users. Anyway, just explain to you quickly about different concepts. I didn't go to details, but I hope you know that we have quite a few ways to measure spatial variation in GIS. And you can see just based on those kind of measurement, we can identify this where it varies strongly. It helps us to identify the influencing factors. And this one helps us to identify potential pollution or mining sites. And this one helps us to understand if we should perform spatial interpolation or not. Okay, that's the concept of the technical side. Now I'm going to talk about a little bit more about opportunities and challenges. We are at the stage of big data, so that's really opportunity. I'm very delighted to see that. We get quite a lot of data sets available now, and it is an opportunity for us. And people are willing to share the data. That's very important now. And specifically at the EU level, we get a whole EU. We have a gamma, that kind of data is available that covers the whole EU country. And I'm working on that data set now. And it's mainly contributed by all the geological surveys in EU. And in Ireland, we have a very high-density geochemical and geochemical survey called telus.ie. And the data, whenever it's available, it's there, freely available, and you can download. And if you're interested in playing some kind of computer games, then we can work on those data whenever it's available. Currently, about half of the country is there now. So I'm going to definitely seriously work on this data set. Because this reaches my area goal now. So I'm going to work on that. And internationally, there's a UNESCO International Center on Global Scale Geochemistry. We are trying to produce the chemical Earth of the world. You know, digital Earth, we get satellite images of the whole world. You can see the digital Earth. In fact, it's a very ambitious program trying to do a chemical Earth. So those are the countries with data already collected. And there are some missing countries. And Canada, I think, says they are unwilling to join. I think when the other countries have joined, I think we will push Canada to join. So to get the whole chemical Earth produced. That's very interesting. And also, so we get increasing amount of data now. And also tools are getting more and more easily available now. We get different software, well, commercial and free data set. But what I want to talk about is the challenges. We get data now. We get software. The challenge, first one is, when we get data, what do we do? That's a major problem for most people. Normally, we can present them statistic tables. Okay, easy to do it. And in fact, there will be lack of problem solving. That's the first issue. It's a lack of data analytic. So that's the first challenge. And here I want to talk about another challenge, is the assumptions. And this one I want to explain a little bit more. The first assumption, when we use statistics, especially parametric methods, there are some normality or some influence of outliers. And this problem, I don't have serious concern because normally people know it now. Okay, unless this person is very, very lack of experience. I believe this is not big problem. But the big problem is indeed as the one I mentioned just now, as spatial autocorrelation. For example, this is phosphorus in Ireland. I declined to produce spatial interpolation map. And the reason is here. Spatial interpolation, what's that? It's estimate the values at unsampled sites. So when we produce the spatially continuous map, in fact, we're estimating the values at those unsampled locations on a grid format, right? Many rows and many columns, then we get a surface. On each of those points on the grid, we don't have value. In most cases, we don't have it. So we have to estimate it. And this is called spatial interpolation. The rationale behind it is that first law of geography. So everything is related to everything else, but near things are more related than distant things. That means the closer ones will make more contribution to the unknown point. Further ones will make less contribution. In fact, that's spatial autocorrelation. And specifically in his paper in 1970, he wrote that, I invoke the first law of geography. And his name is Tobler. And he became famous because of first law of geography. Specifically here, if we want to estimate a point based on those neighboring samples, Those points can be estimated on a grid format, then we get the distribution map. Okay, that's what we are doing. But each of those points will make a contribution. Generally, near ones will make more contribution if we use inverse distance weighted method. Okay, and also we use kriging. Normally, the closer ones will also make more contribution. The fundamental assumption is that they are making contribution, and the reason why they are making contribution is that there's autocorrelation. If the data do not satisfy autocorrelation, then the rationale behind it does not exist. And then you are not allowed to produce the spatial distribution map. What you can do, just present the raw data, original data. That's what you can do. Specifically, you don't have enough data to perform spatial map, to produce spatial map. Okay, that's one challenge I want to talk about. The second challenge is about different scales. We will talk about different factors. So keep that, when you interpret the results, keep the scale in mind. For example, at the national level, we are talking about different land use, different soil type or whatever, and urban area or mining sites. We're talking about those larger scale variation. And smaller scale, for example, in the urban area, we're talking about road density. So we calculate road density. It links very well to the lead concentration in this area. And for a specific site, we are talking about influence just one road. And this side we get a good coverage of a forest here or some trees there. So you get a shield against pollution. And this specific site, in fact, is related to the cover of topsoil. This area is well covered. In fact, it's about 1 meter higher than this site. It's a contaminated site in Galway. So we're talking about very small scale factors if we go to those small scale site study area. And in fact, we have just finished this paper and it's under just a minor revision. So next time I will talk more about the very micro scale variation, what we have achieved so far. And my next step is try to identify the contributing minerals, why they are high there, why they are low there. That's my next step. And you will see something interesting there. Now, other challenges here. That's a socio-economic challenge. That's beyond science. Believe or not, you will find something really interesting here. For example, this one. Well, as I talked earlier, in Ireland, we don't have a strong history of industrialization. Ireland is among the top developing country in the world, okay. And it's mainly based on IT technology, okay. And we don't really have good industry there, a heavy industry. So therefore, pollution is very light there. But I do find a site which is contaminated based on regional survey. Specifically, I found this site because I got quite a few elements. Then I found that site is interesting. Then I found it's a playing ground. Okay, it's a park. So I went back and collected a large number of samples. Because when we report to the government agency, we have to be very careful. So I collected 200 samples. I used an equipment called portable XRF. So we went there and analyzed them. And then after that, I get large amount of data. And you can see the median values of lead. If it's 300, that's really high. So I reported to the local government there. And it definitely is a contaminated site. You can see the values there. And so you already saw that. So I show this map to the local government, as well just city council. And they understand the importance of that. And in fact, this is a historical rubbish dumping site. 2007, then they hired a consultant to do risk assessment. And the conclusion was that this park, South Park, needs remediation, at least 80% of the soil there. So in fact, the whole park needs to be remediated at that time, 2007. But don't forget that in the end of 2007, the Western world, especially Ireland, was hit by financial crisis, subprime mortgage problem from America spread to Europe, and Ireland was heavily affected. So they didn't get money to do the remediation. Then it's delayed, and then 2009 they were preparing for remediation. But in 2014, no remediation is no longer a threat. In fact, they did very simple remediation, and then they said no longer to the public. So what I want to see is definitely this is something beyond science anyway, and I just leave it as a political game there. Okay, that's something beyond us. Okay, the second one I want to talk about is this very interesting one. That's a commercial company currently undergoing in Galway. So we get the in-field variation of nutrient demand. So even though within one land, we will see different level of demand for nutrients. But in Ireland, currently, we have this Green Bible that's from the Department of Agriculture. They have to follow this kind of recommendation to apply their fertilizer. And it's based on mix a sample from this shape, put all those samples together in one land, get an average value. And the problem is that they assume the land is homogeneous. But just now, we already showed the strong variation at different scale. So definitely something is wrong there. So that's what I'm attacking. I hope in the near future, Ireland will improve based on those concepts. So first we see, you can see 100 meter scale, we see the variation there. And then you will see different kind of parameters, not phosphorus. They have a strong variation there. And we are trying to reduce the number of samples required to get the pattern. So that's one of the work we are still working on to minimize the number of samples to keep the cost as low as possible. And this is very small scale, 8 meters. You can see that's a scale. We still get strong variation there. So we believe strong in-field variation exists. Therefore, that's how I got this project called Farm I, and I.farm. That's on the website. And the company is doing that now. I'm just give everything to the university technology transfer office. Then I just do my research, leave it to them. 3 people are working on this company now. And the project is funded by Enterprise Ireland. I was the PI there. And during the project, we also analyzed quite a few sites, and we also showed strong variation there. And the software also provides some kind of mapping function there, just written purely by the technician. But we do encounter a problem. That's the cost. If we require farmers to collect so many samples, or we collect for them, there will be cost. In Ireland, for example, if one sample costs about 10 euros, for one farm, if we need 50 samples, there will be 500 euros. If we get some support and service there, so 1,000 euros, if we ask farmers to pay it, it's quite unrealistic. So we're trying to find a way of how it works. Anyway, those are the concepts, or those are the ideas and problems, the challenges we have encountered so far. So just keep that in mind. Spatial variation exists at different scales, from very large regional scale to sub-millimeter level. Okay. And that's number one. Number two, no mapping. In fact, interpolated mapping is allowed if your data do not satisfy spatial autocorrelation. In that case, increase your sampling density. And also, when you get the data, just keep that, try to be problem solving instead of just describing your data. Anyway, and keep that in mind, if we move towards very far, towards social, then there will be political reasons, political issues, and also socio-economic issues we have to consider. We will definitely encounter them. Thank you very much.